Today we're going to finish discussing section 3.3. As you can see, the three topics we're going to talk about today relate the mole, Avogadro's number, and molar mass to each other. We'll discuss a little bit about what the terms mean, and then it will lead into being able to solve problems relating the mass of an element, the moles of an element, and the number of atoms of an element. First thing, we need to define what a mole is. One of the things that we'll always talk about if we get confused about what a mole is we'll refer back to a dozen. Okay, a dozen is a counting unit. So when we think of a dozen, we think of 12. And so as we're going through this concept, that's something we definitely want to think about. Whenever somebody says a dozen, 1 dozen of something, we think of 12. Well, in chemistry, we don't deal with a dozen of atoms or 2 dozen atoms or 100 atoms. We deal with millions upon millions of atoms. So it's not easy to talk about atoms in such a small unit. So they created a new unit, just like creating a new scale to better manage a quantity in chemistry. So they come up with the concept of a mole. And 1 mole represents a very specific amount of atoms. And it doesn't have to be just atoms, it can be any object. But the number is 6.022 times 10 to the 23rd. Now actually that number is larger, but that is the number that is usually accepted. It can carry out to a lot more digits, but that's what we'll use. That is referred to what's called Avogadro's number or Avogadro's constant. So, just like we were talking about, if we had 2 dozen cookies equals 24, well, now we could say 2 moles of cookies equals quite a few. Okay, we'd all like to have 2 moles of cookies, or I would actually prefer to have 2 moles of pennies, because that would make me, excessively rich. Now, because of Avogadro's constant, what we basically have here is we have a conversion factor. This is our first real chemistry conversion factor in terms of chemistry concepts. So as we deal with a chemistry concept that's a conversion factor, what we have is one of 2 possible ways to relate moles to the number of atoms. So we set up any other conversion factor, we treat a numerator denominator, we try to solve the problem, and so on and so forth. One of the things that make sure you want to know is you can store Avogadro's number in your scientific calculator. Usually we store it as a shortcut of alpha A. That's something that we could definitely be done, and something could be discussed at a later time. So let's do our first calculation then, relating moles and atoms. The first one we're going to do is we're going to be given a mole amount of some chemical, and we're going to try to solve for the number of atoms that would be in that mole amount. Very similar to how we would do a calculation from, somebody says you have 4 dozen pencils. How many pencils do you have? Well, we all know we can say, okay, 4 times 12 is 48. Well, in chemistry, we're not going to use dozen, but we're going to say moles. So we would start out with a calculation that we would be given a certain number of moles. And we are trying to solve for how many atoms are in that sample. In our setup, we would just multiply by Avogadro's number as a conversion factor. And in this situation, it would be Avogadro's number over 1 mole. The reason for that allows us to cancel out moles for that particular calculation. Let me give one other one that we can see here, that just to give you a second example. Let's say we have 3.5 moles of sodium atoms. How many atoms do we have of sodium? So again, we set up our calculation. We have 3.5 moles of sodium atoms, and we multiply by a conversion factor, which is going to get us from atoms to moles. Okay, so we're going to have 6.022 times 10 to the 23rd atoms of sodium divided by 1 mole of sodium. As we can see here, moles cancel, and we are left with a calculation of 3.5 times Avogadro's number. The calculator will come up with several digits. If we look at significant figures, we have 2 and 4, so our final answer, rounded from our calculator, would be 2.1 times 10 to the 24th atoms of sodium. Now what we'll do is, we've gone from moles to atoms, which is similar from going from dozens back to the number of objects. We can go the other direction. Now what we'll do is we'll start off with a calculation that has a specific number of atoms that we're given, and we're trying to find how many moles are in that sample size. And again, to make a comparison, it would be going from a number of objects into dozen. For example, we have 77 pencils. How many dozens of pencils do we have? And we can see here we start with what we're given, which is the number of atoms. We're going to multiply by our conversion factor, Avogadro's number. But what we're going to do now is we have the conversion factor flipped so that atoms of the element can cancel out, and we're left with moles in our calculation, which is moles in our answer. One example to give you here. Start out with 6.84 times 10 to the 25th atoms of strontium. And we want to figure out how many moles we have. So what would we do? We're going from atoms to moles. So 1 mole of strontium goes on top for the conversion factor. Avogadro's number goes on the denominator. And we can get a final answer. We look back in the calculation, we have 3 significant figures in the first one, 4 in the second number, so we can have 3 in our final answer, which would round to 114 moles of strontium. So we've seen one example of each, and your book has obviously several more sample problems to that you can see worked out. What I'm going to do right now is I'm going to put up 2 more calculations that I want you to work on, and we'll kind of come back here in a couple minutes here. I'll pause, allow you an opportunity to work on those, and then come back and we'll check them out some more. Okay, so we'll come back, we'll go over these calculations. Again, anytime I pause it like this, obviously if it's going to pick right back up, what you do is just need to pause your browser there and you can come back and watch the video some more. So our first calculation here, we have 9.3 moles of calcium, and we're trying to figure out how many actual atoms of calcium are in that sample. So our calculation, we would start out, we have 9.43 moles of calcium, and we're going to multiply by a conversion factor that relates calcium moles to calcium atoms, which we know is Avogadro's number. And again, using Avogadro's number as a constant and a conversion factor, we're going to atoms. So Avogadro's number is in the numerator. 1 mole of calcium is in the denominator. Moles cancel. We look at significant figures. We have 3 and we have 4. Our final answer then would be 5.68 times 10 to the 24th atoms of calcium. Now you can see, doing the other example, we're doing the calculation in reverse order. So now we are starting with atoms, and we are going to multiply by a conversion factor so that we end up with moles. To end up with moles, it needs to go in the numerator. Avogadro's number goes into the denominator. Atoms of gold cancel out. And look at significant figures. We have 4 and 4. So our final answer would round to 4.557 moles of gold. Again, there's more opportunities to do sample problems, whether it's in the book or in the mini guides. So just giving you 2 here, you should be able to get you started, being able to do some of the work in the homework.